there, students in my Physical Climatology and Climate Change course. This is Dr. John Schrage, and we are today doing our 5th lecture of the semester, which is actually day 2 about Chapter 2 in your textbook. Just to kind of reiterate so that we understand where we were, last time we were talking all about measurements and measurements of temperature and where official observations come from, both the operational network run by the National Weather Service and the Federal Aviation Administration, which is what you're seeing in this diagram, or like the Cooperative Weather Observings network, which are volunteers that are observing only daily values. You remember we learned about all these different instruments and how the instruments that measure temperature are kept in a instrument shelter, and how that helps the observations actually measure the temperature of the air rather than the temperature of the instrument itself by making sure that the instrument is in the shade and so on. We learned about how that all works on land versus at sea. We use a network of moored buoys that are used to take all kinds of meteorological observations at sea. We also talked about the fact that there are these merchant ships at sea that have a vested interest in good forecasts and so on. So they take our either hourly or 6-hourly observations at sea. We also talked about the fact those are all in situ observations. So they are observations where the instrument is touching what it's measuring. That's in contrast to the remote sensing observations that we can get using satellites, or for that matter radar or instrumented aircraft and so on. But for now we're talking about them in a climate context, which is almost always satellite observations. And remember, the satellite observations, they are using radiation that's being emitted by the surface of the Earth or clouds or whatever kind of problem they're trying to solve, measuring that radiation in space as a way of inferring the temperature, the moisture, the winds, or whatever in the Earth's atmosphere. We talked about the fact that both in situ and remote sensing observations have a potential data problem called inhomogeneities. And an inhomogeneity in the data set is when something happened along the way over a long period of time that makes the observations at the end of the period not consistent with ones at the beginning. Like maybe, for example, the land use around a weather station has changed over a period of time, like urbanization, for example, that might make the data set inhomogeneous. Now, it turns out as long as you know about inhomogeneity problems and have statistical tests to check for it and so on, there's actually ways to correct for that problem. You just have to have the techniques to do it. And as a consequence from that, we now know a lot about how global temperatures are changing. For example, this was a graph I showed you last time where we saw how temperatures have changed. These are temperature anomalies over a period of, I forget, I have a little bit cut off over here, but a period of something like 120 years or something. And you can clearly see the global warming trend in here. And in fact, 9 of the 10 warmest years on record happened since the year 2000. And oh my goodness, we saw all these horrible temperature trends here. You might remember that this graph from last time shows, it's colored in how much the temperatures are changing per decade, and it really helps highlight how the problem is really in the northern hemisphere and really is worse the farther north you go. In later lectures we're going to learn about the mechanisms for this, like the ice albedo feedback and so on, but we're really starting to get a sense of how the problem is distributed unevenly around the world and is worse in the northern hemisphere and is worse at polar regions. So that was all temperature stuff. And temperature has certain advantages, as we talked about, as a marker for global change. It's what we measure most effectively. It is what we have the longest records of, and so on. But today we're going to talk about other aspects of the climate change that, well, maybe the observation record is telling us they're changing, and maybe the observation record is telling us it's not changing. And that's things like precipitation and weather patterns. We're going to focus on precipitation mostly today, but there certainly are reasons to believe that changes in the amount of greenhouse gases in the Earth's atmosphere could be making changes to the Earth's hydrologic cycle. Now, real quick, before I go and define hydrologic cycle, let's be clear here. I'm not saying the gases are changing the hydrologic cycle, like somehow or other having methane in the Earth's atmosphere is going to change the amount of water vapor in the atmosphere. Certainly not directly. It's not like the methane molecules bind to water molecules or something. Sorry, my computer just beeped at me. Rather, we're talking about the fact that the addition of greenhouse gases could be changing the temperature structure, not just the temperature, but the temperature structure of the Earth's atmosphere, as in like how temperature changes with height and so on, all of which might be changing different aspects of the hydrologic cycle. Now, when we say what do we mean when we mean the hydrologic cycle? The hydrologic cycle is a conceptual model that, conceptual model, let's be clear about what we mean by that. A conceptual model, to use a definition from, of all places, Wikipedia, is a representation of a system made by a composition of concepts which are used to help people know, understand, or simulate an object that the model represents. Forget about the next sentence. We're going to be using the word model a lot this semester. I get a little bit hung up on the word model because we use it in so many different ways. For example, later in the semester we're going to be learning about what numerical models of climate are telling us about how the climate will be changing over the next few decades to a few centuries. But this is different. This is more like a collection of ideas, a schematic diagram, okay? We're not attaching numbers to any of this just yet. We are just sort of coming up with broad ideas of how systems should work. That's a conceptual model. Well, the hydrologic cycle, which frankly you've probably been learning about since literally grade school, is an example of a conceptual model. And it's a conceptual model that describes the storage and movement of water throughout the Earth, atmosphere, ocean system. To use the terminology that I got from a particular teaching website, it describes the movement of water between the biosphere, the atmosphere, the lithosphere, and the hydrosphere. If lithosphere is a word that you're a little bit freaked out about, don't be. Lithosphere is, to use a Google definition card, the lithosphere is the rigid outer part of the Earth consisting of the crust and the upper mantle. We often in science just use the word lithosphere to mean the dead ball of rock, okay? You know, the ground, okay? This one specifically says it has to be the rigid part. I don't care how that. We're not terribly worried about the water cycle in the mantle of the Earth or whatever. We're talking about things like groundwater and so on if we're worried about the role of water in the lithosphere. Just in case the word hydrosphere then kind of freaks you out, a hydrosphere is all the waters on the Earth's surface, such as lakes and seas, and sometimes including water over the Earth's surface, such as clouds. That's all part of the hydrosphere. Okay, so our hydrologic cycle, hydro, water, logic, coming to know, how we understand the water cycle is going to be all about the movement of storage of water in the Earth, biosphere, hydrosphere, lithosphere, atmosphere, and so on. And just to take a definition again from the American Meteorological Society's glossary here, the hydrologic cycle is going to be the cycle in which water evaporates. I'm doing this because I want to make sure we have lots of vocabulary words here. Evaporates, goes from liquid to the gaseous state, from the oceans and from the Earth's surface, and is carried over the Earth in atmospheric circulation in the form of water vapor, and then later precipitates out again as rain or snow. And that actually happens pretty fast. Water vapor doesn't last in the atmosphere very long. We're going to learn some vocabulary words about that in just a little bit. It is intercepted by trees and vegetation. I like that word, intercepted. That's a good term from hydrology. Provides runoff from the land surfaces. It infiltrates into soils. Sometimes the vocabulary word there is percolates. It percolates into the soil. It can recharge groundwater. It can discharge into streams like springs that put water vapor back up, liquid water back onto the surface of the Earth, and ultimately flows out down into the oceans where it'll eventually evaporate again. This is the whole business of the atmospheric, let's just say the hydrologic cycle. So here's a conceptual model here. Okay, this is a conceptual model from some teaching website. I forget where I got this thing. But again, you can see, water evaporates off the ocean, is transported over land, where eventually it condenses as precipitation that can be intercepted by the plants in the surface. There can be infiltration into the groundwater. There can be a water table that is storing water in the form of aquifers. There can be surface waters in the form of lakes and wetlands and so on. There is runoff, where water under the influence of gravity is working its way back to sea level. All this good stuff, not to mention atmospheric components of it like clouds and so on. But there's no numbers here. We're not talking about the processes by which any of this happens or the rates at which it's happened. We're just broadly framing up a conceptual model of the hydrologic cycle here. Now, before we move forward with our understanding of how the hydrologic cycle could be changing as a result of the addition of greenhouse gases into the Earth's atmosphere, and what do the observations tell us about that, let's answer a couple quick questions here. Question 1. The oceans, clouds, and soil moisture are all part of Earth's A, radiation budget, B, lithosphere, C, groundwater, D, hydrosphere. Okay. There's definitely a best choice there. I think there's actually two choices that might work, but there's definitely a best choice. What is the best choice to put into that blank? Make a choice for those 4 options and get a little feedback before we move on to question 2.